Good morning, ladies and gentlemen. I'm Zhou Hai from Huazhong University of Science and Technology. The title I report is Multi-Level Forwarding and Scheduling Recovery Technically in Heterogeneous Network for Erasure-coded Cluster. With the rapid development of information technology, fault tolerance for distributed storage is critical. Existing large-scale distributed storage systems have introduced Erasure codes to maintain system reliability and reduce storage costs. Erasure codes have been deployed in Google's, Amazon, Facebook's. Let's introduce Erasure codes. Modern data center deploys Erasure code in clusters composed of the multiplied nodes. The cluster nodes are interconnected via the network coil. By dividing a piece of the data into k origin data block, n-k parallel block are generated by the encoding block of each drive across n distinct nodes. All those attracted in terms of reliability and storage overhead. Erasure code incurs high network traffic consumption and recovery time in fixture repair. Recovery time is always limited by the lowest bandwidth link. The drawback of the conventional techniques lies in a large number of time slots without fully utilizing the association between helpers. PPR deploys a repair into a multiplied operation. Therefore, it takes 2 time slots to repair a block. However, a broken bandwidth of the 2 Mbps of the link D2 to D1 will prolong the recovery time at time slot 1. PPT uses a special bandwidth gap paralysis. Transmission can be used in those two links to bypass the third link. However, we observe parallel transmission will increase network congestion and competition, and also cause a new load bandwidth link. We use the following two observations to illustrate our recovery techniques. We first noticed that idle nodes are very common and have very common reliable bandwidths in distributed systems. As shown in Figure A, helper 1 and helper 2 are supposed to transfer data blocks to the requester. PPR has a low bandwidth of the 2 Mbps of the link helper 2 to helper 1 in Figure B. PPT uses parallel transmission to bypass the low bandwidth link. In our studies, idle nodes are used to bypass the low bandwidth link. In Figure D, we use idle node 4 to construct the two links. We can use the following link instead of the low bandwidth link. We also identify that reasonably scheduled recovery link can well avoid the low bandwidth link. Figure shows the procedure of the repairing node 1 and node 2 using RS64 codes. The two recovery solutions have the difficult lowest bandwidth link at time slot 1. Specifically, the first recovery solution randomly scheduled each node's repair links. However, the lowest bandwidth of the 2 Mbps of the link node 3 to node 2 becomes the recovery brokenness of the time slot 1. In summary, we make the following contribution. We present SMF repairs technique for single node recovery, which use idle node outside the stripe to bypass the lowest bandwidth link. SMF repair can fully occupy the bandwidth resources of the single link without incurring network congestion and competition. We present MS repair technique for multi-node recovery, which find a recovery solution that schedules the parallel repair of the multi-node and transfer data from as large bandwidth link as possible. We also analyze that MS repair can minus the recovery time. Experiment results show that compared to the state-of-the-art repair technique, reduce 36% of the single node recovery time and 55% of the multi-node recovery time. The single node recovery process with SMF repair comprises the following steps. Step 1. Generates the sort-stride single-level forwarding links with a bind-one-aware algorithm. It finds the repair solution with the stride through enumeration, which consumes the least time for each time slot. Step 2. Find the lowest bind-one link at each time slot and use a multi-level forwarding algorithm to generate a non-short stride multi-level forwarding link to replace. Algorithm use either node to bypass the lowest bind-one link by constructing a repair link tree. Let's restart step 1. We enumerate all possibly repaired solutions for each time slot. Compare the lowest bind-one of all repair solutions and select the repair solution with the largest lowest bind-one. For example, we select D2, D3, and P1 to repair D1. The lowest bind-one link of solution 3 is 4 MPS, larger than that of the 2 MPS of solution 1 and that of the 3 MPS of solution 2. Therefore, solution 3 is selected for time slot 1. Step 1 generates sort-stride single-level forwarding links, but the lowest bind-one link will also prolong the recovery time. In step 2, we use eigennodes to bypass the lowest bind-one link by constructing a repair link tree. As shown in figure A, time slot 1 takes 5 seconds because of the link P1 to D1. The multi-level forwarding process, including 2 nodes and a set, the source nodes P1, the target node D1, and the idle nodes I1, I2 form an intermediate set in figure B. The goal is to find a link that takes the least time from the source node, pass through the intermediate set, and reach the target node. Therefore, a multi-level forwarding link P1 to I1 to D1 has been found, which takes 4 seconds less than 5 seconds at time slot 1 in figure D. As NIC and the network caps support full duplex technologies, multi-threading can be used to repair multi-liced nodes. However, random scheduling can cause low bind-one link, prolonging the repair procedure. Based on observation 2, the low bind-one link can be avoided by rational scheduling, parallel repair of the multi-node, and using large bind-one link to transfer data. MS repair can maintain a recovery queue for each fifth node, which shares the recovery task according to the bind-one. MS repair first solves the candidate link bind-one from largest to smallest. Link with the large bind-one will be inserted first to maximize the lowest bind-one link. For example, in step 1, link 3 and 4 is first inserted. In addition, the recovery direction and the task of the inserted candidate link are determined by the following 2 steps. Step 1, such as inserting link 2 to 4 in step 2 of figure. Node 2 is the 4th node. Then link 4 to 2 is built. The link task to repair node 2. Step 2, at step 5 in figure, node 5 in link 5 to 1 with the task of the repairing node 1. When link 6 to 5 is built, the link task is to repair node 2. We have implemented a potato architecture to realize. It uses a global coordinator to manage the recovery operation between requesters and helpers. Erasure-coded is implemented via Erasure and uses TCP sock to realize network transmission. Each node also creates a difficult wrap to process control flow and data flow. We'll show the experimental result of the SMM repair and MS repair where the primary measure is recovery time. By default, we configure 128 Mbps node size, 5 idle nodes. We use Pareto's distribution to simulate the heterogeneous networks. We implement PPR, PPT, random scheduling, and PPCT under the same system architecture by only changing the transmission length of day during recovery. We first use difficult issue codes to measure the computation time to establish the repair solution. Figure A shows the result. Both techniques do not exceed 73 seconds, which are efficient to drive the repair solution. We further provide a breakdown on the recovery time, and figure B shows the ratio of the time taken by different plays during recovery. It also implies that the transmission time is critical to the recovery performance. We also evaluate the SMM repair and MS repair recovery time via NK, including 42, 64, and 96. In Figure A, SMF repair reduced the single node recovery time by up to 33%. In Figure B, MS repair reduced multi-node recovery time by up to 55%. Finally, let's make a conclusion. We first propose that idle nodes are used to participate in recovery process. We propose SMM repair and MS repair technically for single node and multi-node recovery. The result of the two platforms shows that the technique can significantly improve the performance of the node recovery. Thank you.